Hi guys, welcome to this video on the properties of quartic graphs and functions. So, we're learning the properties of quartic graphs. We're going to sketch graphs of quartics and identify their domain and range. Quartic functions are part of higher level polynomials that are needed in pre-calc and calculus. And we're going to be able to use our graphing calculators to graph a quartic and list its domain and its range. Okay, so properties of a quartic function. Quartic functions take the form of y equals ax to the fourth plus bx to the third plus cx to the second plus dx plus e. That said, a, b, c, d, e are all integer values. They all have to be whole numbers. They can be positive or negative, but they all have to be whole numbers. And a cannot be 0. Otherwise, you revert back to a quartic. Special properties of a quartic function, you can have from 0 to 4 roots. So it is possible with a quartic to not have any roots. If you didn't have any roots, you would in fact have 4 imaginary roots. So I'm going to go ahead and write that here. If no real roots, you have 4 imaginary roots. So because a quartic, okay, so x to the fourth, 4 imaginary roots. Let me finish that. This is because x to the fourth can be thought of as x squared times x squared. Let me fix that. Okay, apologies. We can think of x to the fourth. There we go, got the eraser. We can think of x to the fourth as x squared times x squared. Okay, in doing so, x to the fourth equals x squared times x squared. We have a possible 2 imaginary roots here and a possible 2 imaginary roots here. And the 2 imaginary roots added together would be 4 imaginary roots. We remember that x squared can have 2 imaginary roots if it was x squared plus an amount, or x squared, yeah, if it was x squared plus an amount. So x to the fourth could have 4 possible imaginary roots as well. Continuing, you could have 1, 2, or 3 extrema. Remember, when we talk about that, we're talking about local max and local minimums. It is possible for it to have 0, 1, or 2 of those. It will have an absolute minimum or an absolute maximum depending on the direction of the graph. So if it's a negative graph, it will have a maximum. If it's a positive graph, it will have an absolute minimum. Generally, quartic functions don't actually have any real symmetry. And you need 5 points on the graph to properly describe and graph a quartic function. So let's take a look at the basic quartic function. The red quartic function is y equals x to the fourth, and that's what it looks like. You can kind of see that it looks very much like a U. It's a steeper quadratic equation by the look of it. And then you can look at the blue one, y equals negative x to the fourth. And that also is the same shape except mirrored downwards. And if I were to shift the graph up or shift the graph down by adding plus or minus to it, that would change the y-intercept location. So, domain and range of a quartic. So a quartic equation has a completely open domain, a completely infinite domain of negative infinity to infinity. That said, the range of a quartic equation depends on whether or not the graph is positive or negative and has its highest, maximum, or minimum. So let's take a look at this quartic here. Here's a sample quartic. This sample quartic equation, we know that the domain, the domain is as listed above, negative infinity to infinity. The graph goes on for forever in each direction. The range is a different story. For the range, I have a lowest point here. If I draw this all the way across, and this is y equals negative 3. And then up here, the range would go towards positive infinity. So my range would actually be I need to use a bracket, and I'm using it would be from -3 to describe the bracket all the way up to positive infinity, which we would describe with a parentheses. Now, if I wanted to talk, that would be the absolute right here. This absolute minimum. This is an absolute minimum. This absolute minimum is represented in the range. The absolute maximum is infinity. And I do have a local minimum here, so this absolute minimum is also a local minimum. And then I have a second local minimum down over here. And this spot right here on the graph, so I'm going to put that right there for a second. This spot right here would be a local maximum. So I've identified the extrema. I've got my domain of -infinity to infinity, and I also have the range of this Quartic graph. So, sketch the graph of the Quartic function. Here's an example problem I might see with this. Sketch the graph of the Quartic function, determine its domain and range. Where are its extrema? So, I'm going to go ahead and actually type this into my graphing calculator. You would type in x and then up caret 4 minus 4x up caret 3 minus x to the second power plus 10x. And you're going to hit graph. And so, if you go ahead and graph it, if you go ahead and go to the table, this graph is going to move really fast. I do know its domain as a quartic is going to be -infinity to infinity. It is a positive quartic, so I know that the range is going to have a maximum of infinity, but I do have to figure out what is its minimum point. So what I am going to do is go on my graph, and I see -2 is all the way up at like positive 24. And then -1 is all the way down at -6. So in between that, you go all the way down to here. And I'm just going to redo that really quick. And then you have 0, 0 as a point. 1, 6 is the next point. You have 2, 0 as a point. And then you have 3, -6 as a point. And then it goes all the way back up to 4, 24. So it's going to be off the graph at that point. So if I'm going to sketch the general shape, and this is going to be really, really difficult for me with the computer, but I'm going to do my best. The graph is going to go up like this. It reaches this lowest point and then turns around and goes up like this through 0, 0. Comes up to this point, and it turns around at that point, comes back down like this, and then gets up here like that. So you're going to have to forgive my sketch. It's not the greatest, but it is satisfactory for now, just to kind of show the shape of the graph. And if I locate the extrema, the lowest point that the graph hits is down here. So that's y equals -6. So that absolute minimum is going to be the basis of my range, -6 to infinity. And both of these are local extrema. So I'm going to note them as coordinates. So I have one at -1 and -6. That is a local min. So I'm going to put mins. And then I also have another one at 3, -6. So those are my two minimums. And maximum, I have one maximum here, and that maximum is 1, +1, +6. So here's my extrema right here. My local maximum is 1, 6, and then my local minimums are -1, -6, and 3, -6. And that's the graph of the Quartic function with important features noted. I also would note then that I have 1, 2, 3, 4 different y-intercepts. And then I would also note that the x-intercepts, and then this y-intercept down here is 0, 0. So sketch the graph of the function and determine its domain and range. Where are its extrema? So the previous function was in what was known as general form. This function is in what is known as factored form. I can see all of the linear factors plotted out. So what I am going to do is type it in exactly as I see it into my graphing calculator. X minus 1 times x plus 2 times x minus 3, and then that is squared. With 1, 2, 3, and then it counts a second time, 4 factors, I am going to note that my domain as a quartic is going to be -infinity to infinity. The range is a different story. I am going to go ahead and I look at my graph, and I'm going to say, well, I can't really see most of the graph, so I'm going to need to adjust my viewing window. So using the techniques that we learned in class, I'm going to adjust my viewing window to take a better look at the graph. So when I zoomed out, I can see the graph is okay, but doesn't really do the best of jobs, so I'm going to increase my scale. And I'm just going to keep trying, perfecting it. So I'm just doing a couple little calculations here. Okay. I get a good general shape of my graph when I decide to go from -30 to 30 with an x scale of 3 and go from y -30 to y max of 30 by a scale of 3 as well. So I have a general shape of the graph, and that's when I'm going to use my table feature to go ahead and draw some of these points on here. So the graph has some extreme changes. It does have a 0 at -2, as evidenced by this linear factor here. I do have my y-intercept at -18, so I mean all the way down here. 1, 0. 2, 4 is a point. 3, 0. And then 4, 18. And my graph is kind of gone at that point. It should be noted that 1, -32 is the point. So my graph is kind of coming from down here and going all the way down there. I would have adjusted my viewing window, so I would rescale my axes here. And in doing so, this would actually probably be where I'd put my 3 and my 6 and my 9, just to get a better shape of the graph. So that's what I'm going to do. So these are where the points truly lie. This window right here that I am looking at is from 0 to -10 to 10. I'm going to rescale my graph. So what I need to do is erase these points, because what I am going to do is write that these are all by 3s. This is 3, 6, 9, and so on and so forth. So my reader, gets a general sense that these are not scaled by 1s. So when I do that, I can actually graph some of these points. So I do see that one of the zeros was at -2, 0, which would be midway between 0 and 3. I would have 0, -18, which I could actually then graph down here. -18. -1 and -32 would actually be right about here. Because 30 is right above it. And then I go up to 1, 0. 2, 4, 3, 0, 4, 18. So the graph comes down, and then 4 would be here, and 18. And then 5, 1, 12. So it's nice because I can then go in the other direction as well. Values that I am getting off of my graphing, calculator. Negative 2, 0. So the other one is previously up here at 144. So you're going to see your graph come shooting in like this, and I'm going to leave my scales alone. And the graph is going to continue down like this. It's going to turn around. Oop, I missed. So I'm just going to correct myself. Come back up like this. I overshot. Excuse me. Comes down like this, and then shoots all the way back up. So, range, the lowest point, by the look of it, was my minimum of negative 32. So the range would be negative 32 to infinity. Extrema. In this viewing window, I have a couple extrema. I've got that minimum, negative 32, 1, negative 32, negative 1, negative 32. And then I have another extrema up here at 2, 4. And then I have another extrema at 3, 0. And then the graph is gone for forever. So this is my minimum. This is a max. And 3, 0 is also a local minimum. So that's it, guys, for the graph of that. If we were to convert this into general form, what you need to do is multiply them out. So what I can do right away is I can split this into a 2 by 2 multiplication problem and then multiply them. So it would be x times x would be x squared, negative minus x, plus 2x, minus 2. And then I can do x minus 3 squared really quick and get x squared minus 6x plus 9. For the one over here, I'm going to simplify that to be x squared plus x minus 2. And that's going to be multiplied by x squared minus 6x plus 9. And then you're going to need a 3 by 3 box to do that. For simplicity's sake and time's sake, I'm not going to draw the box, but I am going to do the multiplication. I would get x to the 4th when I multiply the first term by the first term. And then the first term by the second term would be minus 6x cubed. First term by the last term plus 9x. And then do the middle of times all three. So x times x squared is x cubed. X times negative 6x is minus 6x squared. And then x times 9 is 9x. And then do this. Negative 2 times x squared is negative 2x squared. Negative 2 times negative 6x is plus 12x. And then negative 2 times positive 9 is minus 18. So if I combine all my like terms really quick, I get x to the 4th. I've got 6x cubed, and x cubed here is going to be minus 5x cubed. I've got a 9x squared. Forgot to put my square in there. I've got a 9x squared minus a 6x squared minus a 2x squared. So 9 minus 6 is 3x squared. Take away another 2x squared is just a single x squared. And then I've got no more linears except a 9x and a 12x to be 21x. And then minus 18. So that would be how I could convert it to general form. Don't worry so much about that one. I think we're going to focus on factored form, but I wanted to show you how to do it just in case. So that's it, guys. In summary, quartic functions are fourth degree polynomials that have unique features. They have up to 4 roots and no general symmetry. The base shape of a quartic is a flatter U-shaped graph, but it quickly stretches into other ones as soon as you add in other hills and crests and things like that. And then we can graph a quartic and stay its domain and range, and we can also convert it to general form. And then make sure, don't forget about all the local extrema. That's it for this video, guys. Thanks for watching. See you in the next one.